Hello and good morning, and today we're going to be going over the multiple choice part from earlier this week. So what I want you to do now is pause this video and grade numbers 1 through 17 that you did. And okay, so now we're going to go over these questions. Just skip ahead to the ones that you missed and you can see how they're worked out. So number one, I'm going to mark up the question just to kind of point out the important stuff. So we have a object is moving to the right with a speed v initial when a force of magnitude F is exerted on it, okay? In which of the following situations is the object's direction of motion changing? So that is going to be important. And the kinetic energy is decreasing. So kinetic energy is going down and the direction of motion is changing. So let's just work our way through that. First thing is direction of motion. Okay, what's the only way I'm going to get a change in direction? Well, if I have something that is going to the right and I push on it in the opposite direction, that's not going to change the direction that its velocity is headed, right? That's just going to slow it down. So I need to have a force exerted on it at some angle that's not parallel with its motion, right? So right away, I know B is out because that's parallel with its motion, and that's it. Okay, so now I look at this piece. What's going to make the kinetic energy go down? So we got to remember, kinetic energy is 1/2 mv squared. The mass of these balls is not changing. It doesn't say that's the only thing. There's only a force that's being applied to it. So I need to figure out which one is decreasing its speed, right? And the only way that's going to happen is if the force has any component of that force is pushing back against the direction it's going, right? Against its velocity. So A right here, A is perpendicular to its velocity. That wouldn't slow it down. Okay, C right here, C is in the direction. There is a component in the direction of its velocity. C would actually make it speed up. So our answer is D. I have a force that's working against its velocity, and I have a force that's going to make it change its direction. All right. Number two. The ball is suspended by a lightweight string as shown in the figure above. The ball is displaced to position 1, so here it starts. The 4 label positions evenly spaced along the arc. So what that means is this arc length between each one is the same. Okay, but between which pairs of the positions is the change in kinetic energy the greatest? Well, this is a conservation of energy problem. Up here, it is all gravitational potential energy, right? So the biggest change in kinetic energy is going to be when there's the most change in gravitational energy. So from our formula sheet, we know that the change in gravitational energy mainly has to do with the change in height, vertical height, that's straight up and down height. So whichever pair has the biggest change in vertical height, that's going to be the biggest change in kinetic energy. It's going to be the biggest energy change, right? So from 1 to 2, from 2 to 3, or from 3 to 4, right? Definitely the biggest change in height is from 1 to 2. So that's going to be our answer, A. All right. For number three, I have not seen a problem like this. This was on the very first AP exam in 2015, and since then they realized the error of their ways, and they decided not to do it. So, if you work this out, this is a good learning experience because if you think about pacing. Pacing, we can only spend about a minute 48-ish per question, right? This question takes a while to work out. So if you feel yourself wasting minutes on a single question, that's where we can get that little kind of alarm in our head, and don't waste tons of time. All right. If it works, put a star next to it. Like if you need to skip it, mark it on your AP exam somehow. Put a star next to it. If on your answer sheet, put like a tiny little dot. Pick an answer that you can, hopefully you can eliminate some distractors, but pick an answer and then move on. If you have time at the end, come back to it. But we definitely don't want to leave any blank. Okay? So I'm just going to uncover what they said in their rubric. And you can read that and do what you want with it. All right? But it is a annoying problem. You can pause this and read that, but I'm going to move on. Number 4, a bus is initially traveling north. Okay? It says the bus starts to turn left without changing speed. The passenger notices that a box on the floor starts sliding to the right. So here's what we need to remember. First of all, Newton's first law. Right? Objects maintain a constant velocity. Newton's first law says that an object is going to keep its constant velocity. It's going to go the same speed in the same direction until some type of net force makes it change its motion, right? So this box, it's originally going north. Even when the van starts to turn, it just wants to keep going north, right? The only reason that things move in the car with you is because there's a force somewhere making it turn. So there's no force making the box turn to the right or anything. That's just the box. That's the van turning and the box still trying to go in the same direction. So there's only one force on this, and that force is from friction. And since friction's job is always to try and stop the motion of an object, if the box is sliding to the right, friction is going to point to the left, which gives us a final answer of B. All right. Moving on to number 5. These are all, again, we haven't actually done any math yet, right? Everything is just kind of conceptual. Here we have 3 different blocks, A, B, and C. The only thing to notice is that C, both of these have the same initial starting velocity. All 3 start from the same height, right? So when I'm thinking about this, and energy conservation kind of comes to mind because I have things dropping a certain height, they're all going to start with the same gravitational potential energy because they have the same starting height, right? All of the A and B, well, let's just go and see what we need to do. Which block takes the longest time to reach the ground? Well, let's think about that. For A, it starts with a 0 y velocity. It has an acceleration in the y direction equal to gravity. Right? So does C. C starts with no vertical velocity, and it has the exact same acceleration in the y direction from gravity. B, so A and C are going to take the same amount of time to reach the ground. But B has this ramp in the way. C can't accelerate the same as gravity because there's this ramp literally in the way slowing it down. So A y is going to be less than g, which means it's not going to speed up as much as the other ones. It's going to be going slower by the time it reaches the ground. Or it's going to take longer, right? So B is the one that's going to take longer. It won't be slower. It's just going to take longer. All right. For 6, it says which one is going the fastest? Which one has the greatest speed? And so this is where you can think about energy conservation. Both start with this, all 3 start with the same gravitational potential energy right there because they're starting at the same height. So all of this initial gravitational potential energy turns into kinetic energy at the bottom. So all the gravitational energy it starts with gets put into kinetic when it hits the ground. So whoever starts with the most energy is going to have the most kinetic when it reaches the bottom, right? Well, A is not moving at the beginning. So A has nothing to work with, right? Just the gravitational energy. B, not moving. C is moving at the beginning. So C has gravitational and initial kinetic energy, and all of that gets put into kinetic at the bottom. So C starts with more energy at the beginning, so it's going to be going faster by the end, right? It starts with an initial speed, so it's going to have a bigger final speed. So C is our answer for which one's going the fastest. Number 7, a ball is dropped from rest and falls to the floor. The initial gravitational potential energy of the ball Earth system is 10 joules. So it's important to know that this is dropped. It's not moving at the beginning, right? So total mechanical energy is equal to all potential energies plus all kinetic energies. That's it. It's just potential energies, gravitational, spring, I think that's it, and kinetic energies. Kinetic translational, kinetic rotation, right? So when it's dropped and it has 10 joules, the whole mechanical energy initially is 10 joules. So there's a ball, right? It gets dropped to the floor, the ball hits the floor, and then bounces up only as high as 7 joules will allow it to go. Now, if you're trying to figure out where those 3 joules of energy went, you are doing it wrong. You're overthinking this, because all you need to know is it started with 10. When it bounced and came back up, it only had 7 joules of energy. So it lost 3. So those 3 joules of energy are no longer a part of our Earth ball floor system. Okay? They might be in the floor or something, but even if they're in the floor, that is from heat. That is not part of mechanical energy. So what was the mechanical energy of the ball the instant it left the floor? Well, the instant it leaves the floor, it has to have 7 joules of energy so that it makes it up to that 7 joule mark. Okay, so the answer is C, 7 joules worth of energy. Number 8, a disk is initially rotating counterclockwise around a fixed axis. There you see these 2 forces right here working, providing a torque on this disk. If counterclockwise is positive, so that's good to know. Okay. Which of the following could show that angular velocity is a function of time? So here's what I need to know. It starts with a counterclockwise angular velocity, right? So I know initial velocity is positive. And these are all angular velocity graphs because it's going counterclockwise, right? That's why it's positive. So anything that has a negative angular velocity to start is wrong. So A, immediately out. B, immediately out. So now I just have C and D to choose between. And so I need to figure out what is the net torque on my object so that I can figure out, is this thing going to be speeding up or is it going to be slowing down, right? So I have 20 newtons pulling on this in the counterclockwise, so positive direction, and I have 40 newtons pulling on this in the clockwise direction, so negative. So my net torque is going to be a negative something, right? It's going to be, there's more force pulling this in the negative clockwise direction than in the positive direction, so that tells me the slope of my velocity graph needs to be negative the whole time, okay? So when I look at my graphs right here, I have C is the only one that has a negative slope the entire time. Oh, what am I doing? Circle and D. C is the only one with a negative slope the entire time. And it asks for angular velocity, right? So that's why it can go be negative. Now be careful. If this had asked for angular speed, then our answer would have been D, because speed can't be negative. But it didn't, so the answer is C. Number 9, we have a box getting pulled on by some forces, and we need to know what its acceleration is. So we know that there is a box. We know that it has a force of 20 newtons pulling it. We know it has a weight from this, a 50 Newton box. That's telling me the weight. Now this is on flat ground, so the normal force will be identical to the weight. And then we have this force of friction right here, resisting the motion, and we don't know what the force of friction is. It could be static friction if the box isn't even moving yet, and it could be kinetic friction. So first thing you need to do is check, is this 20 Newton force strong enough to overcome static friction? Is it strong enough to make it start moving? Okay. So we need to use the fun equation. On your formula sheet, that equation looks like this. And they make it look way more complicated than it actually is. But this is the force of friction. These little bars just mean magnitude, right? So they're not worried about the direction when you're plugging stuff in. Mu is the coefficient of friction, and Fn is the normal force. So we know the normal force is 50. We know mu for each one of these. Static is 0.5, and kinetic is 0.3. So I need to figure out what the static friction force is. So we're going to plug in static friction is equal to mu for static friction right there is 0.5. And the normal force is 50 newtons. So the static friction force, the biggest the static friction force can be, is 25 newtons. Right? Well, it's only getting pulled with 20 newtons of force. So this pulling force, or pushing, or whatever it was, that force is not big enough to overcome static friction, which means that it's never going to start moving. So the answer is A, 0 acceleration. It's not even moving yet. For 10, this is part of angular momentum, and just a quick little history lesson. Remember, linear momentum is P equals mv, right? Angular momentum is a capital L, and we just put the same terms in. Rotational mass, or rotational inertia, is capital I. And instead of linear speed, we have, or velocity, we have angular velocity, which is omega. This is for a thing that's rotating. If I have a thing that's going straight, like this little ball or whatever it's called, struck by a sphere, okay, this is for rotating. If it's going straight, then we know that angular velocity can be found out by taking the momentum, mv, of that thing going straight, and multiplying it by how far away it is from the axis point, r, or the pivot point. Okay, so conservation of momentum. All of the angular momentum initially needs to equal all of the angular momentum at the end. Initially, only this ball is moving, so that's mv d. Actually, they tell us what the momentum is, just p. So momentum of the ball times the distance from the axis of rotation, d, equals. Here now, after the bounce, there's two things moving. There's the ball, and the rod is rotating, right? And that's what we're trying to calculate. We're trying to find what is the angular momentum of the rod. So the ball, we know, is going the opposite direction, and its momentum is pf. So pf, distance d, and it's going the opposite direction, so I'm going to put a negative right there in front of it. So remember, momentum is a vector. Plus the angular momentum of the rod. We don't know what it is, that's what we're solving for. So now just get that angular momentum all alone. Rearrange this, solve for L rod. That's PID plus PFD. Factor a D out. Boom. All right, number 11. We have a spacecraft just placed in orbit. We have a mass. We have a height above the surface. What else would you need to calculate the speed? So if you don't remember this, that's all right. But to get the speed of something in orbit, right, we would need a couple things. You would set this up. Let's draw a picture of it first. There's a planet. There's a little spaceship, and it's going in a circular orbit, right? There's two things you need to know in order to do this. You would need to know the distance from the center of the planet to the spaceship, right? So that's the radius when you're looking at formulas, and there's things like formulas like that. That R is the distance between the center of those things. So we need to know the distance of that, and then we need to know the mass of the thing that's pulling it. So this whole planet, you need to know the mass. Well, we know the mass. It's right here. But the only thing they told us is they told us this distance, the distance from the surface of the planet to the spaceship. So in order to get this right, you need to know what the actual radius of the planet is, so that you can know the whole distance from the center to the spaceship. Number 12. Two carts mass 2m and m approach each other and collide head-on. Immediately collide is making me think some type of conservation of momentum.